Hello, ladies and gentlemen. So now we're going to try to solve this example. Example number 2. It's x cubed minus 4x squared plus x plus 6 equals 0. And we're going to solve it, or we're going to try to solve it with the rational roots theorem, right? Which we saw before. So the first thing we're going to do is we're going to identify the leading coefficient and the constant term, because from these values we will be able to determine the possible rational roots of the polynomial. Okay, so let's do that together. So if we look at this polynomial, we can see that the leading term, the an x to the n, is x cubed, right? Or we can also write it as 1 times x cubed. Okay, we know that this is just a shorthand for this, right? We know that the constant term here is just the 6. Okay. And so that means, for example, that our leading coefficient, the an, is just the 1. The coefficient is the number in front of the variable, right? And so now we have our leading coefficient and our constant term, which we need in the rational roots theorem, right? Remember that the rational roots theorem says that if we have the polynomial equation a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a1x plus a naught equals 0, then if there are rational solutions, if there are rational solutions, they are of the form p divided by q, where p is a factor of the constant term, the a sub 0, which in our example is 6, and where q is a factor of the leading coefficient, in this case, the 1. Okay. We're going to look at the factor theorem's implication in this problem later. Okay. But the most important thing now is the rational roots theorem, because we're going to again construct our p's, we're going to construct our q's, and then we're going to list our possible rational roots, and then we're going to figure out which of those possible rational roots, if any, are solutions to this equation. Okay. So what are our p's? Our p's are going to be our factors of the constant term. And in this case, that's going to be the 6, right? So what are the factors of 6? Well, we know that 1 times 6 is 6, and we know that 2 times 3 is 6. So 1 is a factor of 6, 6 is a factor of 6, 2 is a factor of 6, and 3 is a factor of 6. And I want you to notice that I always put in the positive one and the negative one, okay? Okay. What are our q's? The denominator of our possible rational roots. Those are going to be the factors of the leading coefficient, in this case 1. The only factors of 1 are 1 and negative 1. Why? Because 1 times 1 is 1, and negative 1 times negative 1 is 1. Okay? So our q's, okay, are going to be the factors of the leading term, okay? And what is that? That's going to be just plus minus 1, okay? And so now what we're going to make is we're going to make our list of possible rational roots, okay? Okay? How are we going to do that? We're going to form all the possible fractions with one of these selected as a numerator, and with one of these selected as the denominator. Okay, so you can tell if I choose the positives from the list of p's and the positive one from the list of q's, then I'll just get 1 over 1 is 1, 2 over 1 is 2, 3 divided by 1 is 3, and 6 divided by 1 is 6. So I get 1, 2, 3, and 6 as my possible rational roots there. If I take the negatives from our list of p's and I keep looking at the positive one from the list of q's, then I get negative 1 divided by 1 would be negative 1. Negative 2 divided by 1, that's negative 2. Negative 3 divided by 1 is negative 3. And negative 6 divided by 1 is negative 6. Okay? And then if you continue with that process, you take all the negatives from the p's and you divide them by the negative one, you're gonna re-get this set of values. And so if you try out all the possibilities, you will end up with just this list of distinct possible rational roots from the rational roots theorem. Okay, wait, so let me just restate that one more time. In other words, so here are all the possibilities. I can take positive 1 divided by positive 1, which is 1. I can take negative 1 divided by positive 1, which is negative 1. I can take positive 1 times negative 1, positive 1 divided by negative 1, which would be negative 1. And I can take negative 1 divided by negative 1, which is positive 1. And if I do that for all those possibilities, I will still only end up with these distinct possibilities for the possible rational root. Okay? Okay. So now, the next thing that we want to do is we want to find out which of these, if any, are in fact solutions of this polynomial. But what I want to do is I want to, instead of explicit evaluation, in this example, I'm going to pursue I'm going to use synthetic division. Okay? So let's do that together. So first of all, let us make a table here, x, and we're going to find out if it is a root or not. Okay? And if it's a root, we want to find out the associated factor. Okay? And again, in this case, it's a cubic. So if I were to find one root, and then if my goal was just to solve the equation, if my goal was just to solve this equation, then once I find a root, if I find a root using this list, I would just divide out by that factor, and I would end up with a quadratic, which I could then use the quadratic formula on, right? But here, I want to show the factor theorem, and I want to, show that this list does give us some. Well, in this case, it will give us roots, but I want to show you how to apply the theorem. Anyway, that was just a jumble right there. I apologize. Okay, so what I want to calculate is, I want to calculate f of 1, okay? So that means I'm going to divide the polynomial, let's say f of x equals x cubed minus 4x squared plus x plus 6 by x minus 1, because I know from the remainder theorem that if I divide this polynomial by this factor, the remainder will be this, okay? Let me actually write that down for you so that we can refer to it. So the remainder theorem, just to be completely explicit here, says the following. If f of x is a polynomial, then if k is the remainder obtained when dividing the polynomial f of x by x minus r, right, then we can conclude that f evaluated at r will give us k, right? So if I want to evaluate f, in this case, if we want to evaluate this polynomial at the value 1, we're going to divide that polynomial by x minus 1, okay? And we're going to do that using synthetic division, okay? That will make our work a lot easier. In the previous example, I did it through explicit calculation, because of course that's completely correct, and it's completely something that you can do and that you should do if you want to do it that way. But I also want to show you using synthetic division, because again, I want you to see both aspects, I want you to learn both techniques, and I want you to be confident. Okay, so let's do this together. If I want to divide this cubic polynomial by this factor, I have to put the opposite of this number on the outside of the house. In other words, if I set x minus 1 equal to 0, and I solve for x, I will get 1, and that's the number I put there on the outside of my synthetic division house. Another reason why we're going to use synthetic division is that this will make the evaluation of the function a lot easier and hence a lot faster, okay? So what are our coefficients here? 1, negative 4, 1, and 6. Moreover, we remember, whenever we do a synthetic division house, we have to make sure that our polynomial does not skip any powers of x, and if it does, we have to put in a 0 there, okay? So in this case, we have a cubic, a square, a linear, and a constant term. So all the powers of x in the polynomial are represented, so we don't have to put any we don't have to put in any zeros as placeholders. So now let us perform the synthetic division. I bring down my first number like this, and I get 1. 1 times 1 is 1. Negative 4 plus 1 is negative 3. 1 times negative 3 is negative 3. 1 plus negative 3 is negative 2. 1 times negative 2 is negative 2. 6 plus negative 2 is 4. F of 1 is therefore equal to 4. Okay? Okay. So here, at x equals 1, is this a root? No. What would have been the condition of the value x equals 1 being a root? That the remainder would have been 4, or in other words, to be direct, that this polynomial would have evaluated to 0, right? So is there an associated factor in this case? No, right? Not applicable. Okay. Now, let us proceed to the next item in our list, right? Okay, let's do that together here. Let me erase this, okay. So now we want to evaluate, we want to know what is f of 2, okay? So let's put that on our list. And in fact, we can make our list longer here, okay? 2, 1, 2, 3, 6, negative 1, negative 2, negative 3, negative 6, okay? We want to calculate f of 2, right? So we're going to divide, to do that, we're going to divide f of x equals x cubed minus 4x squared plus 6, sorry about that, plus x plus 6 by x minus 2, right? And so again, we're going to make our division house, okay? And it'll be 1, negative 4, 1, and 6. And if we want to divide by x minus 2, we're going to place a positive 2 here on the outside of the house. Now I begin the synthetic division. This 1 comes down like this. What's 2 times 1? That's 2. Like this. What is negative 4 plus 2? That's negative 2. What is 2 times negative 2? That's negative 4. What is 1 plus negative 4? That's negative 3. What is 2 times negative 3? That's negative 6. What is 6 plus negative 6? That's 0. Here I have a remainder 0. What does that tell me? That f of 2 is equal to 0. And that we got from the remainder theorem and using synthetic division. Notice how fast that was. Okay? So is this a root? Yes. Okay? And is there an associated factor? Yes. The x minus 2. Right? Okay. Now I'm going to show you a couple of implications of this, and then we're going to proceed. So there are several things that I want to show you here. So for example, because we did synthetic division, we actually divided by x minus 2. So what this means is that we can interpret this. Now we're not gonna follow this along all the way to the end. Like in other words, like we're not going to pursue what I'm gonna do here to the end of the implication that I'm about to bring up. But I want to show you that it's an implication. So that, like if you were solving this problem, just this problem as it is, you could do that. So for example, we divided this by this, and so that gives us the following fact. What this says is that x cubed minus 4x squared plus x plus 6, okay, divided by, okay, x minus 2, okay, sorry about this, is equal to x squared minus 2x minus 3. Then of course, so from here, if we were going to factor this as a quadratic, we would ask what two numbers multiply to give me 3 and add to give me, what two numbers multiply to give me negative 3 and add to give me negative 2. Well, I know that the numbers that multiply to give me 3 are 1 and 3. So if it's going to be negative 3, it'll either be positive 1 times negative 3, or it's going to be negative 1 times positive 3. If I add those, I can see that -3 and +1 add to give me -2. So I can see that this factors as x minus 3 times x plus 1, like this. And so what this tells us is that I can rewrite this expression, okay? Let me put a little squiggly here to separate this. X cubed minus 4x squared plus x plus 6. Oops. We can now see that it is equal to x minus 2 times this. Okay. And from the factor theorem, that would tell us that 2 is a 0. It makes this expression equal to 0. And we can see that that's in fact true. But it also tells us that 3 makes this equation 0. Okay. I mean, makes this expression equal to 0, which would mean 3 is a solution of this equation. Okay. We're going to see if that's true or not. It is true, but we're going to verify that here. And this factor, x plus 1, corresponds to the 0, negative 1. So this tells us that this expression will be 0 at x equals -1. Okay. We're going to see if that's true over here. Okay. But so if I was just solving this equation, once I got this root, I would have also been able to infer this extra information, which, as you saw here, I was able to immediately factor and solve the equation. In other words, from what you can see here, we already solved it. Okay. If you multiply this out, you'll get this equation. You'll get this expression, and setting it equal to 0 would be setting this factorization equal to 0. Then by the zero product property, if you have 3 numbers multiplied to give 0, then either this one's 0, this one's 0, or this one's 0. If this one's 0, the x is 2, which is the one we already found. We already verified it through calculation. This one being 0 would mean x equals 3 would be a solution. And this one being 0 would mean that this one is a solution. Okay? Okay? So that's the extra information that we could get. Okay? So that's one thing that's one implication I wanted to show you that we could get from this. Okay? I don't want you to ever do these calculations like blind, so to speak. Okay? I don't want you to be mechanical. Obviously, at the beginning, as we're just learning, you're going to be a little mechanical, but later on, I want you to realize how you can, or not realize, but I want you to combine techniques as you use them, provided they're applicable, so you can solve the problem at hand. Okay. Another thing I wanted to do here before we proceed is I wanted to see by explicit calculation if f of 2 is in fact 0. I only want to do this here so that you can again see that you would get the same result. So if the polynomial is as written over there, how would we evaluate f of 2? Well, f of 2 would be, of course, 2 cubed minus 4 times 2 squared plus 2 plus 6. Okay, let me put a little squiggly here. Sorry about that. I'm sorry this is so compressed. What is 2 cubed? It's 2 times 2 times 2. What's 2 times 2? 4 times 2, 8. So it would be 8 minus, what's 2 times 2? 4 times 4, 16 plus 2 plus 6. Now I'm going to combine these two first. What's 8 minus 16? That's -8, and then I bring down the rest of this. Plus 2 plus 6. What is -8 plus 2? That's going to be -6, and then I'm going to bring down the plus 6, and of course you can see that this in fact is 0. But notice how much easier it was to use this synthetic division. But again, if you want to do it by explicit calculation, there's nothing wrong with that either, okay? Use whichever technique you feel more comfortable with, or if you're using a new technique, like I showed you here, don't be afraid to verify through explicit calculation so you can develop more confidence, okay? And also to double check, you know. Okay, let's proceed. Let's test out the rest of this table, okay? Okay, now we want to calculate f of 3, okay? So if we want to evaluate this polynomial at 3, we're going to divide by x minus 3, okay? And that means we're going to place a 3 here on the outside of our synthetic division house. Okay? And so what would that tell us? Well, so let's do it together here. Okay? I would bring down, of course, the 1. Okay? 3 times 1 is 3. What is negative 4 plus 3? That's negative 1. What's 3 times negative 1? That's negative 3. What's 1 plus negative 3? That's negative 2. What's 3 times negative 2? That's negative 6. And you can see when I add 6 plus negative 6, boop, they disappear, and I get remainder 0, which is exactly what we expected from the discussion we did on the side, right? So this tells us that f of 3 is equal to 0. So that tells us that this is indeed a root. Okay, it's a solution of this equation. And the associated factor is x minus 3. Okay. 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 So now what we're going to do is we're going to evaluate the function at 6. Let's do that together. Okay. If we want to evaluate f of 6, we're going to divide the polynomial by x minus 6, and we're going to look at what the remainder is. Right? That's what the remainder theorem tells us. So let's make our division house again. If we're going to divide by x minus 6, we're going to put a positive 6 on the outside of the division house. And again, the coefficients are going to go inside 1, minus 4, 1, and 6. I bring this 1 down like this. What's 6 times 1? That's 6. What's negative 4 plus 6? That's positive 2. 6 times 2 is 12. What's 1 plus 12? 13. 6 times 13, that's going to be 98. Wait. 78. Okay. Let's do that together here. 6 times 3 is 18. I carry my 1. 6 times 1 is 6, plus 1 is 7. Okay. It's 78. And then what is 6 plus 78? That's going to be 84. Okay. Okay. Yes. So what does that tell us? That tells us that f evaluated at 6 is equal to 84. Okay. And if you notice, I didn't have to calculate any powers. I didn't have to do any of that complication there. Okay. Just basically addition and subtraction and multiplication. So evaluated at 6, is it a root? Is it a solution of this equation? No. And so here, there's no associated factor. Okay. Now I know it might be super finicky to say this, but I think you guys have already seen here that when I say associated factor, I'm talking about a factor of the polynomial on the left-hand side of the equation, right? So, so I just want to make sure that you guys know that that's what I'm talking about. Okay. Okay. And now finally, we're going to evaluate it at negative 1, right? Okay. So let's evaluate this at negative 1. Oops. So if we want to evaluate it at negative 1, then we're going to divide it by the factor x plus 1, right? And so on the outside of the division house, okay, we're going to put a negative 1, okay? And let's separate this number a little bit more so that we can see it more clearly, which one is which, okay? So now I drop this constant down and I get 1. What's negative 1 times 1? Negative 1. If I add negative 4 and negative 1, I get negative 5. If I multiply that times negative 1, I get positive 5. If I add them, I get 6, right? 1 plus 5 is 6. And then if I multiply by negative 1, I get negative 6, right? Negative 1 times 6 is negative 6. And then if I add these, I get 0. By the remainder theorem, this tells us that f of negative 1 is 0. And what does that tell us? That tells us this is a root. Okay? Because it makes this expression, the polynomial expression, evaluate to 0 at the x value negative 1. What's the associated factor? X plus 1. Okay? And now, here, regardless of whether we have the information we got from our little discussion on the side whether we had that information or not, we would notice up here. Why? This is a cubic polynomial, a third order polynomial, and therefore the most distinct roots it can have is 3, and we found 1, 2, and 3 distinct roots. Therefore, we can't have any more roots. Okay? And also, let me see here. And yes, we saw that these are the associated factors of those roots. That means, that is to say, that if we look at this expression, the polynomial expression on the left-hand side, alone, on its own, we can see that this polynomial expression will be a multiple of this factor, and this factor. Okay? And in this particular case, we can see that it'll actually just be the product of these 3 factors. Okay? But it could be that it might be a multiple of that in the general case. Okay? But in this particular case, you will be able to see that it'll be just the product of this. And in fact, let me just do that just as a little extra, and then we'll finish with this example. Okay. So these factors, like let's say x minus 2 times x minus 3 times x plus 1. Okay. Let's say I want to multiply these out, right? I'm going to start by multiplying these out, and I'm going to put that product in the square braces, and I'm going to bring this one down for calculation later. Okay. What's x times x? That's x squared. What's x times negative 3? Minus 3x. What's negative 2 times x? Negative 2x. What's negative 2 times negative 3? That's positive 6, like this. You see? Then I can simplify this term in parentheses. So I get x squared. What's negative 3x minus 2x? That's negative 5x. Okay. And then plus 6. And then I bring down my x plus 1. And then I can multiply this out as follows. What is x squared times x? That's x cubed. What is x squared times 1? That's plus x squared. What is negative 5x times x? That's negative 5x squared. What's negative 5x times 1? That's minus 5x. What is 6 times x? That's plus 6x. And what is 6 times 1? Plus 6. Okay. And then, of course, here we're going to combine the like terms. What is x cubed? So the x cubed is by itself. There's no other terms with an x cubed in there. Now look at this. I have an x squared minus 5x squared. That's negative 4x squared. I have a negative 5x plus x. Plus 6x. That will give us plus x. And then I bring down the plus 6. And you can see that that is precisely the polynomial on the left-hand side of our equation. But like I said, the fact that these are factors of the polynomial expression on the left-hand side does not mean that this polynomial would be the product of those factors in general. It would just mean that it would be some multiple of the product of those factors. Okay? Okay. And let me see, what else did I want to tell you about this? Oh yes, we knew we had to stop when we got to the third root because it was a third order polynomial. And we also noted that if we were actually just trying to solve this equation and not trying to just use the rational roots theorem, if we just wanted to solve this equation, we would have applied the rational roots theorem until we could find enough factors to divide the polynomial down to a quadratic, where we could then apply the quadratic formula. Okay? Often that will save us a lot of time. Okay? But in any case, I also wanted to do this example using the synthetic division because I wanted to show you that you could do explicit evaluation as we did in example 1, or we could do synthetic division as in this example, and I want you to practice both techniques so that you can get good at it. In any case, I look forward to seeing you soon, and thank you so much.